Hello, my name's Nigel Ward, and it's my pleasure to introduce you to the latest in our series of videos. These are brought to you by the volunteers of the IET in Surrey, and you can find more of our content on our YouTube channel, lots of interesting talks. Today we're going to be talking about hydrogen electric vehicles and asking the question, are they the future of driving or perhaps not? So electric cars have held the spotlight in recent years, and that's really because we're moving towards net zero for transportation. Meanwhile, hydrogen fuel cell vehicles have been quietly developed without a great deal of attention, despite some obvious advantages over battery EV solutions such as longer driving range, shorter refueling time and so on. So the question really is, what's holding back hydrogen cars, and do they have a future? To help us answer that question, we have a leading academic in the field, Professor Xuan. He is focusing his research at the moment on net zero energy, circular economy and sustainable development via digital and engineering innovations. His research has significantly influenced the early development of energy and AI as an interdisciplinary field all across the world. He's won lots of awards and prizes for his work, and he's the editor-in-chief of Digital Chemical Engineering and also the founding editor of Energy and AI, two respected academic journals. His main job is Associate Dean Research and Innovation in the Faculty of Engineering and Physical Sciences at the University of Surrey, and that's where we caught up with him for his talk.
My topic today is on the hydrogen electric vehicles today, because when Tim invited me, he said, in your last lecture, you talked about the batteries, EVs, and then there has been some mentions about alternative options of net zero transport, and why not you come here to talk about hydrogen vehicles, and I'm here. So before I go to my next slide, just want to do a very quick survey because today's weather is really not good. So how many of you have been driving here to campus? Oh, quite a lot, almost everyone. So how many of you drive electric vehicle? Oh, quite a lot. But how many of you have ever seen a hydrogen vehicle? Okay, but how many of you own a hydrogen vehicle? None of you. Okay, that's as expected. So I try to elaborate a little why hydrogen. We've been talking about hydrogen vehicle for decades, but why it's not there yet, where hydrogen vehicle has a future, or how was the competitions, if you like, compare with hydrogen vehicles and the normal battery electric vehicles, and hopefully we can initiate some interesting discussions at the end. So I'm going to start with a question mark. How big is the emissions, do you think, from our transport sector? Or in another way of asking, like, what is the percentage of CO2 emission the transport sector accounts for the overall emission of our economy? Rough numbers? So, yes. So it's nearly 30%, depending on when you count it, or which part of the world you count it. But it is significant. It's 30%, and within that 30%, half of it is passenger cars and vans, and then the next largest proportion is trucks and buses, marine navigation, aviations, and then 1% motorcycle, rails, and other transport. So that's the data back to 5 years ago, 2018. So, and we all know that we have the commitment to net zero. And if we really want to achieve net zero, then to be completely decarbonized. So the black curve is where we are now, and depending on different scenarios, we have different decarbonization routes. And if we want to achieve net zero, we have to achieve the interim target by 2033. By 2032, we need to cut emission to 80 tons. You will see an even a steeper curve after that. So it is a very difficult target. We probably have to completely change the way how we take transport. And that's why I think the hydrogen vehicles or the hydrogen as a fuel has been on the table to initiate the discussion. So I try to make my presentation a little bit more generic because it's IET. We have different engineering backgrounds. So forgive me if you are very probably you are a little bit boring, but I will try to deepen the topic a little bit with the presentation. So if we look at the normal way, so I think still we have quite a lot of us driving a traditional ICE internal combustion engine that is powered up by gasoline or diesel. And if we look at really how it works, use octane as an example. So traditional cars burn the fuel. So that's a chemical equation. So you have 1 molar of the fuel octane react with 12.5 molars of oxygen, and what you generate is 8 molars of CO2, 9 molars water, and come up with a bit of heat. So the heat is the energy that drives the piston of the internal combustion engine that gives the power of moving the cars. And if you look at this chemical reaction, it's beautiful, it works, it's very efficient. But the problem is, I mean, there are multiple problems, but here I just point out 2 of them, is you emit CO2, right, when you burn the fuels. And so if translate to our daily life, the normal UK car burns 200 grams of CO2 when you travel 1 kilometer. So that roughly equals to 2 tons per year. So that is your CO2 emission related to your car driving if you drive a internal combustion engine. And then because we use heat or we use the internal combustion engine, then there's also the efficiency limit. Here we call it Caron limit. So that's a thermodynamic limit, which means how smart your engine is. That's absolute limit that determines your efficiency here. And if you look at the equation, that is 1 minus T code over. Not too many parameters, because as an engineer, we always want to play around with parameters to bypass the efficiency or to optimize the system. But the problem here is there's not much parameter that we can play around with to make the efficiency higher. So it's a T, here you see that only 2 parameters. T code, that's the ambient temperature that you cannot do too much with it. And T hot is that operation temperature within the engine. So arguably you can make your engine burn heater. So the higher the temperature, you get higher the efficiency limit, but there has to be a limit because of the materials limitations, and also when you burn the fuel in too high temperature, then there's kind of associated problems such as NOx emission. All these things comes up. So we have to live with a very low efficiency, relatively low efficiency, possibly below 40%, in most of the cases 20-30%. So these are the 2 major issues of our current way of transport using gasoline or diesel. And then people look at hydrogen combustion. So it's much simpler. You can see look at the equations or chemical equations. That's only 2 hydrogen molecules react with 1 oxygen. You get 2 water and heat. So that's good because we have no CO2 emission within that equation. So that's a fundamental, I think, people trying to use hydrogen as a fuel. But if you look at that equation, burn the hydrogen, you are still generate heat and then use the heat to drive your engine, then you cannot bypass the Carnot limit. So people start to think, is there a better way of use energy? So how about if we use electrochemical methods? So electrochemically, you can still have the same, almost same chemical reaction, but instead of generating heat, you can generate electricity. So when you kind of react hydrogen and oxygen, and there's a way that we can release the energy in the molecule, the way of electricity, and then we can use the electricity to drive the electric motor and to drive the vehicle. And the benefit of that is you can get rid of that Carnot limit, and there's almost no limit. The only kind of thermodynamic limit you want to go with is the entropy associated with that. So the overall reaction can be very, very efficient, up to 95% or higher. So that's the beauty of using hydrogen electrochemistry. That's a fundamental chemistry of the fuel cell operation. Okay, so you will see how, right? Because imagine when you put hydrogen and oxygen together, you put a fire on that explode and you get heat, so that's the traditional way. So in order to generate electricity, you have to split the reaction into two parts. So that's the beauty of electrochemistry. So you want to have the anode side and the cathode side. So the way how fuel cell works is you get the hydrogen to be dissolved to be split at the anode side to generate the hydrogen atoms and electrons. And then what happens is the electrons, once it is generated, that's the yellow dot will go through the external circuit. That is in the form, because when the electron moves, that's a form of electricity. And then the hydrogen ions will go through separately with the electrons through a so-called proton exchange membrane to the cathode side. And then at the cathode side, that hydrogen ion react with the oxygen together with the electron that travels through from anode to cathode through the external circuit to generate water. So through that way, you can see the overall reaction is the same, but if you split that into two electrodes, then you can capture the energy in the form of electricity. So that is the fundamental fuel cell. And now we have got the fundamental science right, and with a little bit engineering, you can build a fuel cell car. Okay. So this is the Miura fuel cell car, probably is one of the most famous fuel cell. So basically that's the fuel cell. So the fuel cell is installed in the front part of the car. You of course have some hydrogen tank to supply the hydrogen, and then once the electricity is generated, it will drive the electric motor to drive your car, to drive the wheels. So that is the engineering of the fuel cell car. It's always easier to said than to be done. So if we look back the history of fuel cell, it's almost back to 200 years ago, invented by Sir William Gould, so a British chemist. Actually, is a Welsh chemist. It's kind of the very first prototype. At that time, they called it gas battery. So what they do is to have oxygen gas to be sealed in one of the tubes and the hydrogen gas to be sealed in the other part of the tube, and they insert two electrodes into the tube. Then suddenly they find, or Sir William Gould find that you can generate electricity. So they call it gas battery. So that's Gould was the father of fuel cell, and you can even find Gould's status in the walking path. So it's not far away from the campus in the wider Surrey area. So as I said, it was invented quite a while ago, but unfortunately, benefit to the space program back to 1960s. It's fair because you can find probably 100 better ways of generating electricity as a fuel cell, because it's not particularly a simple process. But NASA saw its potential because in the space you want to have a reliable system, you want to have a high energy density, which at particular applications at that time, normal battery cannot fulfill a requirement. So NASA built the first kind of engineering system of fuel cell and put that in the space shuttle. So actually fuel cell is one of the power sources that sent humans to the moon. So they are very smart. So the fuel cell generates electricity to power some of the service modules. And then if you still remember, the only byproduct from the fuel cell is water. So the water can be used as a drink for the astronauts. So it's kind of a very close, smart, close design of the systems that was used by NASA. And I think that's one of the examples that some of the inventions or technology from the space industry later on translate to the civic applications. So not far away from, this NASA space applications, then people start to think, oh, can we, if we can make the fuel cell that big to that small, maybe we can apply that into a vehicle. So the actually fuel cell vehicle was made by GM in the US. So it was a van, so they called electro van. That is in 1966. So you see, it's not too far away from the space applications. But then there's kind of a silent period, because I don't think the need for net zero transport has emerged since 2020s. So in the early 2020s, we have the first commercial fuel cell vehicle that major players in this field, both are Japanese companies, Toyota and Honda. And then in the 2010s, we start to have the mass-produced fuel cell vehicles, and Miura was one of the most famous ones. So if you ask how many fuel cell vehicles are here on road, on open road in the world, so it's around 56,000 by today. So it's not a small number, but if you compare with how many electric vehicles are on road, that's 18 million. Okay, so then it's only probably like several orders of magnitude smaller, and then you're asking why. So I'm trying to kind of elaborate to start the discussion a little bit more. But there are very strong commercial interests, and a range of car makers, they are investing. They have planned to develop or to sell fuel cell cars in the near future. So there has been some futures of fuel cell cars. Okay. And trying to kind of do some analysis on comparing batteries and fuel cells in terms of technologies, and then also in terms of economics and the wider sustainability implications. So we published this paper back to 2 years ago about the future of fuel cell, proton exchange membrane fuel cells for automotive applications in nature. So I will try to use some of the conclusions from that paper to show you some of the insights on what the future will look like for the hydrogen fuel cells. To start with, I don't want to go into too much technical details, but just trying to unfold a little bit the technical aspects. When we put BEV, that's battery electric vehicles, FCV, that's fuel cell electric vehicles, to see the differences and trying to make some fair comparison. So the storage and storage media, of course, for battery vehicles, that's typically lithium-ion batteries. And the latest version of battery electric vehicles, they also use other battery type, but lithium-ion is a mainstream up to date. Fuel cell vehicle is as a storage medium. And then if you look at the specs, the specification of a kind of a car, the vehicle power sources, what is the important kind of parameter specifications? The first is the energy density, because it determines how much energy you can carry in your car, and then that can translate to how long you can travel, okay, with a single charge. So the energy density, actually, fuel cell takes a wing. So the battery normally has 200 watt-hour per kilogram, and the fuel cell has slightly higher. And of course, then in terms of refueling time, batteries always takes hours. Of course, now the fast charging, you can probably charge maybe 50-60% of your battery in 20 minutes. It's improving, but still, fuel cell is the same as when you charge hydrogen, is the same as when you charge fuel. So you just lift nozzle and charge hydrogen to a car, so that takes only minutes. So again, fuel cell wins to some extent in terms of refueling time. And also, one of the considerations is the low temperature operation. So battery has serious problems. So those of you who drive electric battery probably know that in winter time, your mileage will decrease significantly. And for fuel cell, it's not a problem. So for fuel cell, the problem for low temperature is really the startup. So we have done quite a lot of research trying to develop strategy for fuel cell vehicles to start at a lower temperature. But once it is started, there's no performance limitations or indications. And fuel cell have demonstrated working very, very well up to minus 30 degrees Celsius. So that will kind of be good for most of the UK climate. And in terms of efficiency, here we only talk about the efficiency in your car. So later on, I will show some analysis of the wider life cycle energy efficiency. But in terms of energy utilization in cars, battery EV is quite efficient, normally 90% energy efficiency, and fuel cell is slightly lower, but still quite higher than the internal combustion cars, about 60%. And in terms of infrastructure, of course, you need charging points, batteries, and you need hydrogen stations for fuel cell vehicles. To some extent, they are both new infrastructure to the current transport infrastructures, but you can see like the battery ones are developing much, much faster than the hydrogen stations, which I will go into a little bit more details later on. And this is a quite interesting diagrams about comparison between battery and the fuel cells. Sometimes we argue that one has to win, but we know that the future energy will be a mix. So zero sum will be a mix. You have to have multiple technologies to tackle different areas. And if we compare battery and the fuel cells, battery seems to be winning when you have a smaller kind of vehicle size or driving range, typically of the city mobility. And then when you go into those long haul or heavy duty vehicles, then fuel cell will win, because as you can imagine, fuel cell is kind of a chemical devices. There's a chemical flows, hydrogen, oxygen, water flows within the devices. So you have to have some sort of additional pumps, valves, and then when you have all of these things, there's a scaling effect. So the bigger the better the system. So to that extent, there's a common consensus that fuel cell will probably be performing better in these trucks, heavy-duty vehicles, but battery might have a better solution for those smaller, light kind of applications. Then there's a bit of intersection, the overlap with those medium-range ones. Okay, so, and we also discuss, because one of the questions we always try to ask ourselves is how good the technology is, and how good is good enough, right? Because you can always kind of improve the technologies and make it better, but at some point there should be some target and direction of travel, and at some point we will find that the fuel cell is competitive enough for two battery vehicles or two internal combustion engines. So in that Nature paper, we also discuss where we can improve. Again, I don't want to go into too much details, but this is just another way of showing the fuel cell in a slightly probably more beautiful way. And if you really unfold that fuel cell, you can see that the key component are the bipolar plate. So that's a plate that will assemble everything together and provide the flow channel for the hydrogen and oxygen or air to flow. It's normally made of metal. And then it is the gas diffusion layer. So that's a porous layer currently mostly made by carbon paper, but there's some discussions of using alternative materials to improve the performance. And then because it's an electrochemical reaction, so you normally need catalyst. So that's the catalyst layer, that's a layer between a proton exchange membrane. So a membrane is just like a plastic membrane, but it's made of a special material people call naphthalene. So the function of naphthalene is to allow the hydrogen atom to transport through the membrane from the one side to the other side, while don't allow the other molecules to be passing through. And the catalyst is normally made of noble metals like platinum. So that's one of the issues that we want to address because platinum is expensive. Okay, so we discussed in that paper that how far we want to go in each of these individual components, so that when we assemble them together to make a fuel cell cheap enough or high enough to compete with other options. And also, there are kind of other agencies such as the United States Department of Energy, US DOEs, or the European Unions. They have targets of fuel cells. So we feel that, or the research community feel that if we can achieve that ultimate target, then the technology will be competitive enough in the market. So if you look at how far away are we from those ultimate targets, so the first column is the 2015 status, which is probably already 7-8 years ago. The interim target is an interesting one, so that's the 2025 target, and that's probably exactly where we are now because the fuel cell area is developing very, very fast. So that kind of reflects where we are now. So if you look at that, for example, the peak energy efficiency. So we are now, 7-8 years ago, we're at 6%. We are now probably at 65%. Ultimate target is 70%. So improving, it's not so far away. Power density, okay, so there has been some improvement. We still have a way to go. Specific power, so we've already final targets. And then cost. I think cost is one of the key factors that people want to drive down because essentially you want to make your car to be cheap enough to attract buyers. So there's different ways of measuring the cost. Here we use US dollars per kilowatt, net kilowatt. And back to 7-8 years ago, it was 53 US dollars per kilowatt. And we've reduced to 40, and the ultimate target is 30. And then the durability. So we've been involved in a number of research projects. We can confidently say that currently we can run the fuel cell in 5,000 hours. So that translates to about 10-year lifespan if you in your car in a typical duty cycle. So 10 years is roughly enough, but the ultimate target is 8,000 hours. That translates to 15 years, which is definitely enough. Probably the other part of the car will die out before the fuel cell dies. So you can see there has been quite a lot of achievement. There has been progress made. We are close. We are very close. Sometimes we already achieved the target. For some other target, there's still a way to go, but people are confident in achieving these targets. And ask, okay, these are the engineering kind of numbers, how that translates to if we want to buy the car. So you can actually buy a fuel cell car if you wish. Even in the UK, I just look at the Toyota Miura website this afternoon before I'm here. So this is a quite decent car you can buy from 550K. So it's not too expensive, right? And then you can top up your hydrogen tank with around 70 pounds, and that will give you 400 miles. So it's not too bad. Probably it is competitive with your diesel cars, your petrol cars. Probably it's slightly worse or not that competitive with your EVs, because EVs normally give much cheaper electricity charge for a certain mileage. But in terms of the vehicle price and also the mileage that it can give you, it is a decent choice already. Okay, so then I think I try to give you to paint a picture technically. There has been a lot of discussions or development in recent years that make fuel cell cars close to market, or is already in market, given the competitive options compared with other electric vehicles. But we want to now, in the next part of my presentation, to put that kind of technology into the wider systems, to look at some of the limitations we are currently facing today. So the first question we're going to ask, or people, the first thing people normally ask is where the hydrogen comes from, because you're going to use hydrogen to power your car. It is clean at the time of use, because if you still remember, the byproduct is water, so it's clean in terms of carbon emission, but it's also clean in terms of kind of air pollution. You don't have all these nasty SOx, NOx emitted. But if you look at the system from the big picture, you have to ask where hydrogen comes from, right? So currently, the majority of the hydrogen comes from the steam reforming of natural gas. And interestingly, people trying to, I don't know if you've seen this before, but nowadays people trying to label different colors into different ways of making hydrogen, so that it comes with kind of the hydrogen rainbows. Here I only show 5 colors, but if you look at the literature, there are probably 10s and 20s colors, and no one, I don't think there's any single person can name all the colors of different hydrogen production ways. But here, just name a few. So currently we are largely producing gray hydrogen, so that is hydrogen from steam reforming of fossil fuels. And blue hydrogen is the same way, but you try to capture the carbon dioxide in the hydrogen production process. We are trying to shift to the green hydrogen production, so that is through the electrolysis of water using renewable energy. Okay, so that's just the opposite way of fuel cell electrochemistry, by the way. And there are other ways of hydrogen production, like yellow hydrogen, pink hydrogen. The pink hydrogen is the one that through the same electrolysis process, but using the nuclear energy. Okay, and there's quite a lot of other ways of producing hydrogen. So different ways of producing hydrogen will have different carbon footprint or environmental footprint, and not all the hydrogen production methods are low carbon or sustainable. And then if you look at this figure, that, for example, black or brown, that was a hydrogen one, quite high hydrogen footprint. The gray hydrogen high. See that is captured, but actually from the life cycle point of view, it's still high. And green, and then depending on how the system is configured, is still. So if you look at that, and what I'm trying to help you here is to give you the diesel emission. So you can see that not all the hydrogen production are low carbon. Many of them has a higher carbon footprint even than the diesel. So if you use hydrogen fuel cell vehicle, the hydrogen is from, for example, gray or blue hydrogen, and it does not automatically translate to a sustainable solution. So that's one thing that we need to consider. Then the other thing we need to consider is the hydrogen storage. So we talk quite a lot of hydrogen fuel cells, seems like a high tech, and we tend to forget about the hydrogen storage, about the tank, because people think tank, oh, that's just a cylinder. It is a low tech thing, but it is not. Because if you look at in theory, hydrogen is probably one of the most energy dense molecules, so it gives you if you especially in terms of mass, so that's gigajoule per kilogram, it is probably 2 or 3 times higher than diesel and the petrol, and of course, order of magnitude higher than the battery solutions. And because hydrogen is a gas, so in terms of volumetric energy density, it's not as high as diesel and the petrol. They are liquid, but if you compress them or liquefy them, they still offer comparable, even higher volumetric energy density than most of the battery solutions. But that's in theory, that's a hydrogen itself. So in reality, you have to have a hydrogen tank to put all the hydrogen into your car. And then when you add a tank together, the whole picture has changed. So these are the kind of the reality. So if you put all the hydrogen storage system together, then you will probably end up with something lower than diesel and gasoline. So again, this is a US DOE target. So by 2020, we are here so that you can kind of compare with other technologies, or especially diesel and gasoline, and this is ultimate target 2050. See, once we consider the storage systems, the energy density will be much, much lower, but still kind of comparable with diesel and gasoline. It will not give you kind of the mileage panic if we do it well. And also, I think one of the key problems is the infrastructure, because many of you think, oh, it's a decent car, but where can I charge my hydrogen? So there has been quite a lot of development recently, because hydrogen has been mentioned many times in many national energy infrastructures or strategies. And guess how many hydrogen refilling stations we have worldwide? It's around 81. So that's a number I get today. So there's a kind of a website, hydrogenstation.org, that gives you a real life numbers of hydrogen stations. So the blue ones are the ones in operation, and the green dots are the ones has a solid plan to be operated in the next 2 years. So you can see some areas of the world we have decent amount of the density of hydrogen hydrogen refilling stations. That's the European region and some of the East Asian. And if we try to kind of zone these two regions a little bit larger, you can see it is mostly Germany here in the Europe who want to develop the hydrogen network. So they have the target to have enough hydrogen stations in the highway system, so that if you drive a hydrogen vehicle, you can get recharged within your mileage range. We have a handful of numbers of hydrogen stations in the UK, and there will be more in the coming years, but the numbers, of course, is orders of magnitude lower than the electric charging point. And also, like Korea and Japan, they put hydrogen electric vehicles as, of course, at a higher priority than the UK as option. So they are developing quite a lot of, they've already developed quite a lot of hydrogen filling stations. So this is a picture of the infrastructure. So now I try to kind of, so the last part is about the sustainability, because I think one of the motivations why we choose electric vehicles or hydrogen vehicles is we want to achieve a sustainable future. And how to assess that is we use the so-called life cycle assessment technique. So instead of assessing a snapshot of a process, we take the full life cycle viewpoint of an electric vehicle. So if you look at the sustainability of the vehicle, you need to look at the fuel cycle. So that's how you burn where your fuel comes from, how it is produced, how it is burned, and when it's burning, what is the emission. So that's a fuel cycle. And also there's a vehicle cycle. So what is the raw materials of making that vehicles, and what is the environmental impact when you produce that raw materials and converting those raw materials into the component of your cars, and the end of the life, we need to have a proper disposal of the vehicle. So each step has certain environmental impact in terms of carbon emission, but also in terms of, for example, ecology, toxicities, or environmental, wider environmental impact. People have done quite a lot of LCA, life cycle assessment. And the hotspot, I mean, there are problems for both battery EVs and the fuel cell vehicles. The issue for batteries are really the cobalt and nickel. So we've heard a lot of stories recently about ethical mining of cobalt and nickel. And the battery EV are very clean at the point of use, but when you try to get this nickel in other part of the world, it has generated quite a lot of problems, both environmentally and ethically. Fuel cell has a different problem. It's mainly the platinum, so that's the one that used as a catalyst for the electrochemical reactions. So one of the efforts we are trying to do is to lower the amount of platinum used in the fuel cell systems, and with the technology become mature and mature, we can use less and less platinum. So trying to reduce the environmental impact. So if we consider everything into account, as I said, the fuel cycle and the vehicle cycle, we can see that there are quite a lot of LCA studies, by the way, in the literature, and there are slightly different results reported. But I think the consensus here is, if we compare the hydrogen fuel cell vehicles and electric battery vehicles, within the technology, so that's your current car, hydrogen fuel cell perform slightly better in terms of sustainability than the electric vehicles. But then with the future technology advancement, of course, both vehicles, the environmental impact will be lower in down, and then probably in the future, electric vehicle will slightly win hydrogen vehicles. But also, there are other studies. So, for example, in this study, they compare the battery EVs and the fuel cell EVs, and sometimes some studies say the fuel cell is slightly better and battery is slightly better. But I think the overall story I'm trying to tell is both are quite sustainable solutions, especially if you compare with the current gasoline engines, and especially the electricity and the hydrogen is from renewable sources. Okay, so the last part is just come back to the title. So hydrogen fuel cell vehicle, does it have a future, or is it a future of driving or not? So I hope I have given you enough information that you can make your own judgment, but I just want to throw a few different voices, because there's no definite answers, unfortunately. Different people have different voices. For example, the European Climate Foundation. So here I'm just trying to give you, there's a lot of predictions how the fuel cell, what's the role of fuel cell to be played in the future transport mix. The European Climate Foundation predicted by 2050, probably more than 30% of the new car sales will be hydrogen fuel cells. And this is a conference paper. They're even more optimistic that they feel that more than almost half of the new sales by 2050 will be fuel cell cars, which I personally don't believe. And also there's some negative voices, like this report, the Future of Electric Vehicle report by Bloomberg. You can see in their prediction by 2040, so that's the blue. Only takes just a slice of the future mix of the new vehicles. So I think if you drill down into the methodology, how they produce these models, because as an engineer, I always want to see the data and the method and the model to produce these results. So they use different data, they use different models, and most importantly, they use different scenarios. So I think my consensus is the more environmental, the more straighter net zero kind of push you want to go, the more you will see hydrogen fuel cell in that picture, because probably that will go back to the picture that I just shown. in order to decarbonize the transport sector, you have to consider both the city mobility and the heavy-duty vehicles. And I think fuel cell will definitely play an important role in the heavy-duty vehicles, but also in some part of the city mobilities. Okay, so I think that's the end of my presentation, and I hope you find it useful. And this is a quite kind of interesting, as there's a lot of debate, so maybe you will agree or disagree with me, but I'm very happy to open the discussions or questions.
Thank you very much for such a fascinating and informative presentation.
Electric vehicles are heavier, which obviously has implications for infrastructure, multi-fuel car parks, and also tyre particulate emissions. How does the weight of hydrogen cars compare with internal combustion and electric?
So you mean that in terms of weight?
The weight of the car, yeah.
Yeah, so I think that's kind of been shown in some of these diagrams that have been shown before. So it's essentially the kind of the energy density, because we have different ways of measuring energy density. So you can measure in terms of volume and in terms of weight. So hydrogen has again. So this is kind of the energy density in terms of weight. So electric vehicles are slightly heavier. Not that heavier, so if you compare 200 and 300. So I think a fuel cell vehicle can be potentially lighter. But then you also need to kind of think, because the energy storage part is only a proportion of the whole kind of vehicle, right? So in the current technology, fuel cell wins a little bit marginally. So
yes, yeah, I'm thinking about the weight of the whole car with everything, all the tanks and all the parts you need. So are they significantly lighter than electric?
So you mean heavy duty?
Yeah, so the total weight of an actual car on the road compared to internal combustion and electric?
So it's almost the same. It's almost the same. Yeah. It wins a little bit. Yeah.
Okay. Can I? Thank you very much.
Thank you. Yeah, great presentation. Thanks a lot. You quoted the 200 to 300 comparison between a battery vehicle and a fuel cell vehicle. That was kilowatt hours per kilogram, if I understood correctly. Was that kilowatt hours after the efficiency or before? Because
That's after the efficiency.
After the efficiency. Thanks very much. And so, well, why is the weight comparable? Why is the weight of a fuel cell vehicle not a third of the? Why is it not 2/3 of the weight of a battery electric vehicle?
Yes, because the energy storage weight is only a proportion of the whole kind of weight of the vehicle. Yeah.
Thanks very much.
Yes, thank you very much for an enjoyable presentation. I'm just wondering if there have been any assessment of safety, relative safety of the different types of...
Yeah, that's a really hot topic, especially right after the fire of the Luton Airport, I think. So hydrogen, if we talk about hydrogen, it gives the impression that it's a dangerous gas, but it is not actually. So there's a lot of hydrogen safety studies, so it is kind of a topic that we have been studied 200 years, and we are relatively kind of know the safety aspects of the hydrogen. So it's actually, people may not believe, but it's actually safer than the internal combustion engine, because in order for hydrogen to explode or to burn, it has to be mixed with oxygen. And because hydrogen is gas, when there's any leakage, the hydrogen will go into the air. So it will not spill a kind of inside the vehicle that will generate kind of fire compared to normal kind of liquid fuel side. And also because of the kind of the hydrogen is so easy to kind of to emit, there is less, of course there's a risk, but the safety is well controlled, and there's a common concept that hydrogen vehicle is safer than normal internal combustion.
So there's no spontaneous combustion of hydrogen, there has to be...
no, it has to have oxygen to get combustion.
But some heat or something else as well to make it...
You have to have oxygen, because if you remember the fire triangle, so it has to have a fuel, have the oxidant and the heat. So you have to all three to get.
Yeah, so there's a certain amount of heat that you need to apply in order to get the combustion.
Yeah, but you still have oxygen. So and the beauty of hydrogen is it's a gas field, so it will emit very, very quickly, even there's a leakage.
And what about battery EVs? How do they compare in terms of safety?
Yeah, it's a highly dependable area. Some people feel it's batteries car are safe, but you see all this news coming out regularly. So I'm not a researcher on battery, so I cannot really comment. But there has been a lot of research recently, especially in the UK, to address the battery safety problems. So I think there are two problems here. One is the public perception that, and also the real technical challenges for battery safety, which I'm not familiar with.
Would you say they were approximately equivalent to internal combustion, do you think?
Well, I think it's difficult to say. I think there are different levels of risk or different, yeah.
Okay, thanks.
Thank you.
Okay, we've got one here. You mentioned about the efficiency of the process and trying to get it up to 65%. And you also mentioned that chemically, obviously, it's a very efficient. You can get very high. So what's the limitation on the 65%? Where in the processes are we limited?
Yeah, so that 95% is a thermodynamic limit. So that's kind of the highest you can go. Anything beyond that will kind of it's I guess the second law of thermodynamics. But there are different losses in different kind of systems, because first of all, when you kind of have these electrochemical reactions, there are losses kinetically, which means, for example, not all the hydrogen are reacted, and then within the reacted hydrogen, not all the energy is generated in terms of electricity. Some are emitted in terms of heat. And then when the electricity is generated, there's also transmission loss, which is small compared to the internal combustion engine. So then you add all them together, you get kind of 60% roughly.
You say that the efficiency of the fuel cell system is about 60% compared with 90% for a battery system. That leaves you 40% of your energy that you have to manage in some way. Does that give you a thermal management problem in the vehicle? And can you use that for any useful purpose, such as heating passengers in cold weather?
Yeah,
and hence gain an advantage over the battery vehicle where you haven't used battery power for that sort of thing?
Yeah, that's a really good question. So the two challenges in fuel cell management, one is thermal management, the other is water management, because you generate a lot of water, so how to get rid of the water efficiently from the fuel cell is one of the problems. There's also thermal management issues, as you rightly pointed out, but technically is less challenging than the water management, as you can imagine. But there is thermal management issues, and I think that kind of emerging studies, as you said, how can we utilize that part of the heat, for example, for air conditioning or for other part of the vehicle where heat is needed.
Thank you.
Thank you. Thanks for a very interesting presentation. You put it across very clearly. Thanks. Couple of questions. very quick one. What really caught my eye was one of your charts where you were showing different ways of producing hydrogen. And yellow hydrogen, which I think you explained as solar produced, looked incredibly inefficient compared with everything else. I wonder why that is.
Yeah, I mean, that's because the definition of different colors of hydrogen kind of varies quite a lot. So some people use yellow hydrogen as kind of the solar in-grid, and also someone just defined yellow hydrogen as just using the kind of off-peak electricity to generate hydrogen. I think because of there's some sort of ambiguities of defining that part of the definition of the hydrogen, that gives you kind of the impression that the solar one is not as efficient as people are thinking of. So my impression is if you have a solar farm and then you use a solar farm to generate hydrogen, the carbon footprint will be lower. But if you are just using the kind of the off-peak electricity from the grid to generate that hydrogen, then the carbon footprint can be potentially very high.
Okay, thank you. And for me, one other question, which is, I've read that something that fuel cell vehicles are very unsuited for is very short duty cycle journeys because of the time of the energy it takes to get them up to operating temperature. Is that correct? And are there things being done to address that?
No, so I think it was an impression, but I think that has been largely addressed. So if you look at, for example, the Toyota Mirai specifications, one single charge you can drive 400 kilometers. So that's a decent driving range, isn't it?
And so my question is a bit the opposite. For typical sort of city driving that is perhaps only the journey only being a couple of kilometres, that they're very inefficient when used in that way because of the time to reach operating temperature. Is that correct?
Kind of. There is an issue because, as I said, fuel cell do have that kind of the start phase, but it's not that kind of, because, for example, we have the U.S. Department of, and I didn't show that part, but they have the target for the fuel cell to reach the full operation within kind of 3 minutes. So if, for example, if you only drive less than 3 minutes, and that's inefficient. But yes, anything longer than that will be.
If you look at the market today, and you look at electric vehicles, there's a sort of sweet spot in smallish SUVs, like the equivalent of the Honda Jazz, which claim a range of, say, 300 miles plus minus 50 miles, and an efficiency of about 4 miles per kilowatt hour plus minus, say, 0.25. Could you sort of hazard a guess as to what the equivalent sweet spot might be for hydrogen and when it might come about?
Well, that's a difficult question to answer, I think. So there's always, the competitions, right, between the batteries and the fuel cells, and you see a lot of advances in battery vehicles in different ways, like the fast charging, the long range. So some of the typical issues of battery vehicles no longer exist, like the mileage anxieties or things, and then people also trying to address like the battery mileage in cold weather. So there has been a lot of kind of progress recently, and I think it's also largely driven by the market need, because there's so many battery vehicles. There's such a big market, so that drives money on the R&D of battery vehicles. So that's kind of, you see a lot of progress on that. But there are also quite obvious progress in the fuel cell vehicles. So as I said, as I presented earlier, there has been targets. So if we meet that target, I don't have a clear picture how those ultimate targets will finally translate to the performance in terms of mileage, in terms of efficiency. But I think the common sense is if we achieve the US DOE target by 2050, or the sooner the better, then the whole technology will be comparable to the battery EV.
You touched a little bit on the use in HGVs, I noticed, although it's a bit out of the scope of this lecture maybe. But is it true to say that the potential for use in HGVs, where there's perhaps not much alternative, would be a driver, in this whole technology area to get it, to improve the take-up in cars, the lower end of the scale? Yeah. Of course, we'll see it in buses as well.
Mm-hmm. Yes, that's largely true. So I didn't show, actually there are two sets of US DOE target. The one I've shown is for city mobility. So there's a different set of targets for HGVs. And there's a group of people, actually I think there's a kind of, they call it consortium for hydrogen HGV. So it's a very hot research area, and there's some big initiative in this area.
Could you say a little bit more about hydrogen combustion? Mm-hmm. A few years ago, JCB, I believe, produced a fuel cell digger, which was a sort of fairly mighty beast. Mm-hmm. But I understand that JCB are now directing all the development energy in hydrogen combustion.
Mm-hmm. Yes, so it's kind of seen, you're absolutely right. So we've been seeing, because it's almost regarded as kind of a dead research area for hydrogen internal combustion, but there has been seen a number of kind of bump back of this area. Then people start to re-look into the area, and companies we see kind of investment into the hydrogen combustion, internal combustion vehicles. But I think the problem is, the good side is it's a relatively well-known system because we've been researching combustion for many years. So I think it's just replacing the fuel between hydrogen and gasoline. It's still difficult, but it's relatively kind of easy if you want to reinvent the wheel. I think for hydrogen combustion there are two main issues. One is it operates at very high temperature. It has a much higher temperature than the diesel combustion. So there's much higher material requirement, so that normal kind of stainless steel cannot tolerate that high temperature. So you have to use expensive materials to build the engine. And also the operating high temperature means you have a lot of NOx emissions. So that's kind of a side problems of the hydrogen combustion. And also it's about the efficiency, because any internal combustion engine cannot bypass 40%. But I think still the people still find niche applications of hydrogen internal combustion in some applications. So that area start to be kind of receiving some interest in recently.
Yes, I believe JCB claim that they have solved the problem of the high temperatures and the NOx production by able to burn at much lower temperature.
Yeah.
Thank you for including a section on the whole life cycle of vehicles. It's really a bit that quite often when people talk about electric vehicles, they're focused on, but nothing comes out of the tailpipe. It's all fine and dandy. Interest in the kind of the next step. One of the big struggles at the moment is that a lot of EVs are coming to the end of their life cycle, and what do they do now? And some of the battery recycling systems are not that great at the moment. They're just kind of shredding it and then trying to extract whatever they can from it. And I guess potentially an advantage of the hydrogen fuel cell is that the only thing that's essentially different to, you've not got the chemistry of the battery, you've got the fuel cell, which is in many ways a simpler construction than a lithium-ion fuel cell. So, as I assume from the comprehensive presentation you've given us today, there is a lot of research into that next step as well.
Yeah, exactly. So I think there's a lot of life cycle assessment studies on that, and you're absolutely right. Fuel cell has a simpler or less hazarded material compositions than batteries, which make it easier for the end-of-life treatment, or essentially offers slightly kind of a lower environmental impact from the vehicle cycle point of view. But there are also quite a lot of research on the battery recycling. So I think one day people will solve that problem, and then that will bring down the environmental impact of both technologies.
So how difficult is it going to be to set up the fueling stations around the country that there seems to be a complete lack of at the moment? And then how sure can you be that your hydrogen is going to be sourced from a reasonable source?
Yeah, how difficult it will be, it's technically not difficult. I think it's all about money, right? So it's an investment, and I think it's a national strategy whether we want to go for purely electric vehicle routes or we want to have some sort of hybrid or mixture, or in some part of the country then we can see there more emphasis on the hydrogen route. So as long as you have the clear national strategy and you have the investment comes in, then it's technically not an issue to roll out the hydrogen filling station. And also hydrogen is so important nowadays in the UK, so I think in the future the big picture is all hydrogen should come from renewable sources. Yeah.